So first of all, you guys need to understand that sound is basically a longitudinal wave. And how longitudinal waves are formed? So longitudinal waves are formed in a medium which vibrates parallel to the energy transfer. So when you look at a longitudinal wave, you guys need to understand, let's suppose you're looking at a drum, and suppose this is the drum skin. So when you hit the drum skin can actually go forward and backwards. So it's basically going forward and then it's going backwards. And when it does, it pushes the air particles forward and backward as well. So sometimes the air particles would go closer to each other, and then sometimes they are going to be far away from each other, like that. So just looking at that, you might realize that basically it forms a pattern like this, which here this is called compression, and this section with the particles far away are called rarefaction. You got my point?
Yes, sir.
So you can actually find the wavelength of a wave like this by simply including one whole compression and one whole rarefaction. So this distance that you're looking at could be the wavelength, and if you're looking in terms of time, that would be the same, right? You could also do it by looking at the center of a compression and the rarefaction, that is also a wavelength, and of course the center of a rarefaction and another rarefaction, that would also be a wavelength. Is it clear, everybody?
Yes, sir.
So compression means that in a compression, particles are closer and offer a region of high pressure because they're basically moving like this. In rarefaction, particles are moving away and offer a region of low pressure because there are less particles and they're moving away, so that's why. All right, you just need to remember that. Now the next thing you guys need to remember is that sound cannot be transmitted in a vacuum, and that is the reason that it requires a medium to transfer energy. When I say medium basically means something like a solid, liquid, or a gas. Now let's look at some mediums and let's see how we can basically how we can show that the sound does not travel in vacuum. So the speed of sound in steel is basically about 5,000 to 6,000 meters per second. The speed of sound in water is about 1500 meters per second. The speed of sound in air is about 300, in fact, let's be more precise, 330 to 350 meters per second. So as you can see, the denser the material is, the sound basically travels faster. Understood?
Sir, what is the first one?
Steel. All right. So it is fastest in solids and then slowest in gases. So that's how it works. All right. Any questions now?
No, sir.
All right, my friends. Now, so then the question remains that how can we prove that sound cannot travel in a vacuum? And we can prove it by a simple experiment. And the experiment is called the bell jar experiment. So in the bell jar experiment, what you need is there is a jar which is enclosed, and then here you have a bell that's connected to something, right? So bell, and then this is a vacuum pump. So basically what it does is it can basically pump out the air to cause vacuum inside. Now the simple experiment explains that when air is inside the jar, we can hear the sound of ringing bell. But when air is pumped out of the jar, we cannot hear any sound of the ringing bell. Simple, right? Okay, Farzeen, is it clear? Moiz? Soha, Zarish?
Yes, sir.
Okay. Interesting. Now, let's move forward. So, keeping that in mind, then, we also need to basically find the speed of sound in air, and we got a couple of experiments to do. So one of those experiments is basically using light, and that's something very, very interesting. So suppose you guys, one person has a flare gun, and he basically stands at a predetermined distance, predetermined long distance d, from another person who has a stopwatch. Now, what you guys need to understand is that naturally the speed of light is way faster than speed of sound, right? So when this person fires the flare gun, this person sees it and starts the stopwatch. And then almost instantly the light reaches there, but the sound travels much slower and reaches the person after a certain amount of time, and then that person can actually stop the stopwatch to determine the time that the sound reaches him. All right, so we can write about this too. And we say, okay, when the first person standing a long distance away fires a flare gun, the other person starts the stopwatch by looking at the flash. Okay, then what happens is he stops the stopwatch when sound of the gun reaches him. Using speed equals to distance, which is in this case it is d, divided by time on the stopwatch, we can calculate the speed of sound. Is it clear?
Yes, sir.
All right, now what you can do is the experiment is repeated multiple times to ensure an accurate value of speed. So you can do it like repeat and take average, right? Please let me know if you do not understand this. Anaya and Caroline, anything you guys did not understand. Okay, done. Should I go forward then, everyone?
Yes, sir.
Okay. So the next experiment is using echo. Now, echo is basically a reflection of sound. So, when the sound reflects, you hear your, the sound twice. That's what echo is. So what you're gonna do is, so you're gonna stand in front of a wall, and the wall should be plain enough. So plain wall, and then one person, basically, usually people use wooden claps like this, and the other person who's standing right beside this person has a stopwatch in his hand, right? So they stand, both of them basically stand at a predetermined distance, like this. Okay. Now what you guys need to understand, that the moment this person claps, the second person is going to start the stopwatch. The sound is going to go like this. It's going to hit the wall, and then the sound will basically reflect back. And when he hears the first echo, he can stop the stopwatch, and that would give him the time for the sound to basically go to this side and then return back to them again. Do you guys understand this? So we can say, standing in front of a plain wall, the first person claps, second person starts the stopwatch. What happens then is, the moment the echo, in fact, let's write the first echo is heard, he then stops the stopwatch using speed equals to 2 times the distance, because it's an echo, it has traveled distance d once and distance d again, divided by the time. We can determine the speed of sound. And basically what you can do is, you can actually repeat the experiment multiple times to ensure an accurate value of speed. Understood? Okay, when the meeting ends, please rejoin the same link. What my point?
Yes, sir.
Perfect. So you guys have written this. Should I move forward then?
Yes, sir.
Okay. Now, so the third sort of experiment is using a cathode ray oscilloscope. Cathode ray oscilloscope, we're going to study this later as well. But right now, I just want to tell you, it's just the same thing where if you go to an hospital, they put a, that machine that shows the heartbeat, right? That's just like it gives waves. It's the same. So what you're gonna do with this is, you're gonna, suppose this is the CRO, in short we call it CRO. And then you're gonna plug two microphones to it. So suppose we plug one microphone right here. Let's call this mic 2, and then we're gonna plug another microphone right here. Let's call this mic 1, and we also need to know the distance between them. That's the distance between them, D. And then we need a sound pulse generator. So basically, pulse of a sound is just one single wave. That's like this. So when the sound basically is generated, you guys need to understand that the microphone 1 will show, the moment it reaches mic 1, it is going to show a reading on the screen like this. And then after a while, when the sound basically reaches the second mic, after some time, it would show another peak like this. Do you guys understand this? Now, from the screen itself, from the CRO, we can determine the time. Okay. And then we can find the speed of sound. This is the most accurate way of doing this. So number one, we can say that two microphones placed a distance apart are connected to CRO. When a sound pulse is directed towards the microphones, each displays the wave after a short while on the CRO. We can find the time interval using CRO. And now what you're going to do is use speed equals to the distance, that is d, divided by the time that we took from CRO to find the speed of sound. Is it clear, everybody? Any questions? Okay, Shawis, everything is clear. Iman,
Yes, sir.
Hussein,
Yeah.
pretty cool, my friends, then. Okay. Okay, now let's go. So now generally I'd say that sound, not all sounds can be heard by humans, but we do have a human hearing range. All right. So the human hearing range is basically between 20 hertz to 20,000 hertz. That's the human hearing range, right? Now, if you go below this from 0 to 20, that's called infrasound. Some of the animals hear that. And beyond this, it's called ultrasound, and that has certain uses that we want to do. Okay? Everybody understands this? Or no? All right. So, ultrasound can be defined as sound that has a frequency greater than 20,000 hertz. All right. Now I just want to write you I want you to write the last thing, and then we're going to explain one of these. So the uses of ultrasound. I'm gonna do them in detail tomorrow. The first use is basically non-destructive testing of materials. That's what it is used for. I'm gonna explain it in detail later. It is also used in medical scanning, and then it is used in finding depth or distance from time and wave speed, which is basically a small word. It's defined as sonar. Okay, please write this down and then we will see. Okay, is it clear? Any questions now?